Morning. Well, it is my pleasure to be coordinating this competition. So today we will test the second beam of the students' benchmark competition in the scope of the Cice 2025 conference. So we see the beam is already or is ready to start the test. So we still need so we still have 1 minute to start. I'm asking my collaborators to be here. Mansour, okay, we will start. Okay, so, well, this second beam is totally is a twin beam, and if I remember you, this beam is flexurally strengthened with 3 NSEM laminates, so laminates of cross-section of 1.4 by 20 millimeter. So we have 3 laminates in the bottom in soffit of the beam, and these lines that we see here are in the alignment of the existing steel stirrups, and in the this zone, well, this is the region that will be monitoring by DIC, by digital image correlation, to evaluate the maximum crack width in the cracks that will be formed in this region, as well the average crack spacing. So we see a line, horizontal line in the bottom of the beam that coincides with the geometric center of the existing steel reinforcement, the flexural reinforcement. So we are just starting, only some seconds. Well, only to remember you that this is the second beam. The first one was tested in last Monday, and after to post-processing the results of these two beams, well, we will be able to verify what will be the participants with the best score. So we have two classes of participants, those that participate with analytical models, and another group with the numerical models. So we have a award for both groups, but only after the results of this test we will be able to obtain the score, obviously. Okay, so hey guys, is it's already loading? Not yet. Okay. So 10 seconds to start. So we will have two collaborators, it's two PhD students, Mansour and Rosbe, that will help to mark, to analyze the cracks. So they will analyze the cracks and indicating the corresponding applied loads. Okay, so it's already started. So it's okay. So the load, João, 30 kilonewtons. Okay, so well, we are not yet. Obviously we have not yet any cracks, since the load is lower than the cracking load. So I remember that the shear span, this shear span has 1.5 meter. The distance between the distance between the applied loads is also 1.5 meter. So it's a 4-point load configuration. So this is the logos of the organization that are being supported this competition. So besides the Cice, we have the support of the company Aga Technique, also the support of IZZ, the University of Minho, IST, LENEC, and the laboratory, the last, that is our laboratory, where we are. So I have here the two collaborators uh, to 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 mark the cracks when they will appear. Up to now, no cracks has formed. Um, in this stage, the beam, the response between the load and the deflection is linear elastic. Then after crack initiation, as you know, the stiffness will decrease due to the crack propagation. And then at a certain moment, we will have again another decrease in stiffness when the flexural reinforcement start yielding. Above this loading label is the contribution of the CFRP laminates, so that will allow the beams to continue supporting load. Well, we have also the collaboration of the, the steel, the flexural steel bars due to the hardening behavior of these steel bars. So in this phase, as you see, we have an aluminum bar that is supporting the LVDTs. This system allows to exclude the register of parasitic displacement. We have also strain gauge that are, so this is the, as you can see here, so the notch corresponds where the CFRP laminates are installed. The first crack has appeared. 70? 77, so at 77 we detect the first crack. So load. Another crack very close to the localization of a stirrup. As you see, is a vertical crack, is flexural cracks as expected. Another one is formed, as you see. Load 83 kilonewtons. Okay, so the cracks are progressing. 85. So after post-processing the results, we will see that at this stage the stiffness in terms of load deflection of the beam is decreasing due to this crack formation and propagation. So another crack now is okay, it's connecting to 90 kilonewtons. So is in the this crack is in the localization of the load section. So all the cracks up to the moment was formed in the pure bending region. Pure bending region, if you obviously if you neglect the effect of dead weights of the beam. So apparently no cracks have formed up to now in the shear span. So okay. So as I remember, 100 kilonewtons. So we in the top. So in the top face, as you can see, we have a strain gauge to measure the compressive strain in the concrete, while in the bottom we have a strain gauge installed in the steel as well in the CFRP laminates.
108.
So using these trains, we can also evaluate the curvature of the cross-section. So having the moment versus curvature,
111.
we can derive the tangent or the second flexural stiffness.
115.
115 kilonewtons. So it's amazing that up to now, well,
117.
no cracks were detected in the shear span. Okay. Now first crack.
119.
119, 119, 19. Okay. So we have now, but this, as you can see, is a vertical crack. So consequently, is flexural crack.
Load. 125.
Oh, so 125. So now more cracks is being formed in the shear zone, in shear span. Okay, but they are still vertical.
130.
130 kilonewtons. Well, we, as is visible, so we have up to now,
134.
we have detected up to now 3 main cracks in the, so 3 in this zone where Mansour
137.
is marking, but obviously in the other, in the other zone when we have DIC, so it will, another 3 cracks
140.
would have appeared, and these are the main, the principal cracks. So then we have what we designated secondary cracks, like this one. So secondary cracks,
145.
and in general this crack does not progress, it stay limited to the bottom region. Luís, tens aí uma caneta que essa, yeah, sim, preta, que funciona melhor.
150.
No, for Rosberg. For Rosberg, because but it's not working. Okay.
155.
Okay. 155. 155. Well, okay, I'm going to the other face. To the other face of the beam. A moment. Okay.
164.
Well, in the here it's more difficult to detect the cracks, but it is now we have here a crack in the shear span, so a flexural crack in the loaded section, and then, well, so it's one flexural crack, another flexural crack. So this is the distance between the cracks. In reality, we can detect the deformation. Well, 1, 2, 3, 4, 5, 6. I think is 6 cracks in the pure bendy region. So one in the alignment of the loads, and then so cracks in the alignment of the loads, and then more 4 cracks in the interior of this span. going around. So
190.
190, 190. Well,
Down.
193.
193.
Load.
194.
Okay, since the load is increasing, well, the maximum bending moments, or the bending moment is also
Load.
increasing,
198.
and then obviously we start having more cracks closer to the support. So we are also,
Load.
200.
well, verify the occurrence of inclined cracks.
Load.
202.
202 kilonewtons. Apparently the flexural cracks have not yet
Load.
207.
progressed um, progressed to the
210.
to the to the flange, because we have not yet detected any crack in the flange, but
Load.
but
216.
but soon is this will happen. So
Load.
218.
218. So we see that, well, after the formation and propagation of these three main cracks in this part of the intermediates of the zone between loading points, so other secondary cracks are being formed but do not progress.
230.
Okay, so
Load. Load.
235.
235.
Load.
238.
238. It is more difficult to see
145.
cracks in
146.
the zone where we are resisting the crack width and crack spacing with the IC.
200.
46.
Now, okay, so finally the the crack that is in the loaded
Load.
section
150.
entered in the flange at the load label of 246. So this monitoring is quite nice, or this type of information is excellent for calibrating advanced numerical models, because we have well, the
255.
localization and and the load label, uh, and therefore it's with this information we can in reality verify the predictive performance of the models. Um, so even uh,
Load.
complex finite element
257.
models have real difficulties to estimate crack widths.
Load.
259.
So the force deflection is more simple, but the entities for SLS, for service limit state, is more complex. So mainly the models based on smear crack approach, where we don't have the explicit concept of crack, so the cracks is
Load.
distributed,
261.
not explicitly simulated. Okay, we are in 268,
Load.
262.
262. So the second crack, so another flexural crack is also progressing through the flange now. I
Down.
265.
remember that in this competition, crack width will be measured at the label of
265.
the flexural reinforcement. So where we have this horizontal line, so using the IC, we will evaluate, we will measure the crack width in each crack crossing, each crack crossing this
268.
line, and then the maximum will be the maximum of the measure. Okay, so it is
Load.
270.
270, 270. Who is remember? Do you remember what was the maximum load that we obtained? 300 and 390. Okay.
Load.
So in the previous beam, the maximum load was 390 kilonewtons.
Load.
273.
273, 273. The three cracks that we have, that are we are marking in this in the zone between the supports, between the loading, between the point loads, have already all of them progressed through the flange. So the most recent is in the middle at a load of 270 kilonewtons. So as you see, as closer are
Load.
the cracks to the support, as incliner, as inclined due to the predominance of the shear load. Remember, the shear is constant in this shear span, but the bending moment is increasing from 0 in support up to the maximum in the point in the loaded section. So the principal stresses are rotating, and then,
280.
well, the crack is also rotating, so when it's progressing to the top, they initiate in the soffit as a vertical,
281.
but then the inclination is changing during the loading process. So
282.
282. Okay, 282 kilonewtons. The crack width in the principal flexural cracks is already significant.
Two
285,
Note.
285.
285 kilonewtons. Um, so this is the bottom of the beam. Um, so you can see the bottom of the beam. So we see the three laminates. It's clear their localization and well, the cracking that is formed. So we see the position of the strain gauge. Okay,
Note.
289.
as canetas são novas, mas são a qualidade, não escrevem nada. Elas são muito bonitas, mas deve ser. É. So we see the propagation of the shear cracks crossing the stirrups is quite nice. So, well, for instance, this crack progressed through in between the existing stirrups. So the major part of the cracks are formed in between, as you can see, even this one. So it's progressing, and then, well, so in the bottom is it vertical, but coinciding with the localization of the crack. Only this one is crossing the stirrup, and now this one is also crossing. Well, the crack opening is
Note.
increasing
295.
in the primary flexural cracks. It's quite visible now. So I should remember that we don't have any horizontal reinforcement in the middle of the web, so we have only in the bottom and in the flange.
Note.
298.
It's progressing, the crack is progressing to the loaded region, 298, so we are approaching to 300. I remember that the previous one, the maximum load was 90, 390 kilonewtons.
Load.
99. $300.
300 kilonewtons. Pode ser. Bom,
Load.
301.
wow. This incline crack is now also progressing to the loaded region. The crack closer in the shear span, but closer to the loaded section, so we can see that the crack width in the almost in the center of the web, the crack width is already significant, so maybe a 0.2-0.3 millimeter. Now we are using another color for the markers because the previous ones is not anymore working properly. We are using now blue color, 305 kilonewtons. So these are new secondary cracks. But we continue to have only 6 primary cracks in the region between the loaded sections. We see now, even in the region where we are using the IC, now is clear the localization of 3 cracks, one coinciding with the loaded sections, and then another 2 is very visible now. So consequently we have 1, 2, 3, 4, 5, 6. So we have six primary cracks, and then, well, secondary cracks. Secondary cracks is being formed at this stage, even at this stage, due to the bond phenomena. So the bond of the flexural reinforcement, and so it's transferring by bond tensile stress to the surrounding concrete, and consequently new cracks are being formed. For me, it's not, I cannot, I'm not able, or I'm not capable to indicate what will be the failure crack, because all the 6 seems at this stage to have the similar crack widths. I want to remember that in the previous one, so all the CFRP laminates fell in tension, have a rupture, so we were able to mobilize the tensile capacity of these laminates.
Load. 315.
315, 315. Okay. So the crack width is already very impressive in some cracks. So due to safe reasons, when we will approach the load of 350, I will ask my collaborators
Note.
to interrupt
317.
this marking process of the cracks. Manzur, are you supporting the beam? Okay. Okay. Yeah, the cracks has an incredible, it seems an homogeneous crack width. For a human being, obviously, I'm not able to distinguish a difference between
320.
1 millimeter and 0.8 or something like this. But the crack width is in this beam is really high. Due to the stiffness of the bottom region, uh, the crack width seems larger in the middle of the web than at the level of the reinforcement. So we can see here, so the crack width here in the middle. So and when we compare to the bottom, so it's at the level of the reinforcement is a little bit smaller. So we can see the same in this beam. So we have the crack width in bottom, and then when in the middle is clearly higher. Um,
325.
3,
325.
25. Okay, I will show again the crack pattern in the bottom, so you can see the crack pattern. So it's a lot of cracks. So when due to the debond process between the laminates and surrounding concrete, it is formed this huge number of micro cracks. But obviously, when the cracks where the cracks coincide with principal flexural cracks, the crack width is higher. Okay, so well, I think it's better now to move away. So as I indicated, due to safe reasons, now we will not interrupt the process of country marking the propagation. Well, I believe that now the propagation is minimum and no more new cracks will be formed. And so now the main cracks will be opening. So
330.
330 kilonewtons. So even this crack we see, so the crack width, look, so the crack width in the bottom is much lower than the crack width in the middle region of the web of the beam. So will only indicate now the load label. Now the increase of load is now much smaller, so the rate of load increment is much smaller because at this stage the flexural reinforcement has already healed it, so the increment of loads is assured mainly by, or almost exclusively by, the laminates, and well, a small contribution due to the hardening of the steel bars, and obviously also in the concrete in the top, so that is in compression. So crack opening continues to open significantly. João, load
335.
335. Okay, so it's really, the increase is really small or smooth. Okay, remember again, the maximum load of the previous beam was 390 kilonewtons. I'm localizing now. I'm fitting or this principal flexural cracks. Because, well, in any moment the laminates that are being crossed by these main cracks will attain their tensile capacity, and obviously they fail. And then the maximum 340, and then when the tensile laminates, when the laminates fails in tension, the load carrying capacity of the beam will have a drop up to the label supported by the the flexural steel bars. Okay, crack width continues to open smoothly. It's very visible, the cracks in the IC region, the three cracks, and then the secondary cracks. And go around to see the other face of the beam. Well, it is very clear the localization of the cracks, so inclined cracks, mainly due to the predominance of shear. Then the inclination of cracks becomes almost vertical, and then in the pure bending regions the cracks are vertical.
350.
350, 350 kilonewtons. Well, we will see if the beam will attain well the same load carrying capacity of the previous one. As we know, the concrete is a heterogeneous material, and but we will see. We never know. Okay, the crack width continues to increase. The curvature obviously also increasing the curvature. It will be nice or after obtaining the moment curvature. And using force method or displacement method, it will be quite easy to estimate the force deflection, even with a simple analytical model. Estimating the force deflection is relatively simple. Crack width and crack spacing is another story. It's much more complex. Even the strains are not so simple, because the strains depends significantly on the relative distance between the localization of the strain gauge and the cracks. But we will see when we will compare the predictions with the experimental results. So the crack width is incredible in these two cracks. The third crack, the crack width is much smaller, so it's very visible, the difference. So the load that is close to the loaded section and the following one, the crack width is much higher than in the third crack, the crack that is closer to the center. And the same happens apparently in the big region, so we see clearly a crack with a, so this crack has a crack with much larger than, in this case, larger than the one that we have in loaded section. I'm not reporting the evolution of the load because now it is very smooth, this evolution. So now this crack, the crack closer to the load section, but in the shear region, the crack width is also increasing significantly. So the crack is in between the two stirrups, is not crossing the stirrup. So, well, 360 kilonewton. Remember again the previous one, 390. Well, the laminates, I imagine, they are suffering a lot, mainly in the region that is being crossed by the principal flexural cracks. Well, also in this region, I imagine, is not too far away of the tensile strength of the laminates. We are approaching to the failure loads. In the sections that is being, in the sections crossed by the flexural cracks, we have a gradient, a significant gradient of tensile strain and consequently of tensile stress, and then so uh, the, the, the laminates fails in this region. 365. Well, it seems that the difference between the two beams in terms of load capacity, well, at this moment will be, it seems that it will be, the difference will be very small. It's hard for me to believe that it will exceed because the crack width is quite significant in the in these two in some principal flexural cracks. Okay, we start. I don't know, but it seems that I heard something. I don't know if it is some local 370. Okay, so look for the crack width, the evolution of crack width in this from the bottom to the top of this crack closer to the loaded section, but localized in the shear span is very, so the crack width is, I don't have any doubt, I think it's more than 2 millimeters at this moment in the middle, but in the bottom when crossing the reinforcement, the crack width is much smaller. So when we are analyzing now this crack,
373.
this the flexural crack in loaded region is similar. So closer at the level of flexural reinforcement, the crack width is much smaller than in the middle. Well, we also see that some secondary cracks, so now is converging is in the main crack, so it's progressing towards the main crack. So some we can see that some new secondary cracks, but so very close to the main crack is formed. So this is due to the process of the bond between the flexural reinforcement and surrounding concretes. Okay, so 375 kilonewtons.
375.
Since the localization of the damage is in this principal flexural cracks, the crack within the others cracks is stabilized. So at this moment, all the uh, all the damage is localized in these main flexural cracks. So we can see the teeth representation that we have in the bulletin. For the more sophisticated model, the beam is discretized in a series of teeth
380.
uh, um, crossed by the flexural reinforcement and also for the CFRP, and taking the equilibrium and the kinematics of these teeth between neighbor teeth, we are able to determine the evolution of the force in each component during the loading process. So it's a little bit more complicated model, but we can obtain more accurate results. It will be nice, it will be very interesting to verify the capacity of this more sophisticated approach to predict the average crack spacing. Because if we do not predict the average crack spacing with sufficient rigor, then the model obviously will not be able to determine properly the tensile stress in the reinforcements. But we will have the opportunity to analyze the predictive performance of this approach, not only the one that we have in FIB, but also in the other standards. 385. 385, we are approaching to the, oh my God, it's opening significantly. So we are approaching to the load carrying capacity of the previous beam. So now it's okay. So we now start listen noise. So it's the end. Okay. It's amazing. Oh, and okay. Oh. So we have several moments of the load loss of load carrying capacity. So which means that the uh, the laminates have rupture in several cross sections. We still continue to. So what is the load now? 217. So, okay, we will maintain, we continue to increase a little bit, but obviously the laminates have fell in this zone, so in several locations. So now the contribution is due to the existing steel reinforcement. And it is amazing because I think the difference between the load carrying capacity of this beam and previous one is very, very small. It's 4 kilonewtons. Vamos ver como é que essa carga vai evoluindo. Qual é a flecha? What is do you know what is the deflection?
128.
128. And okay, what was the maximum load? Do you know the maximum?
It was 395, 96, 85. The last that
85. I think it's 85. Yeah. Okay, so now since the beam is fell, so I think we can interrupt because now the load carrying capacity is mainly due to the existing flexural reinforcement that is already yielded. So now eventual increments of load is due to the strain hardening, but now the bond conditions even between the existing steel bars and is quite destroyed. So João, I think we can stop. Okay, we can stop. Okay. Okay, we can. I will look. We will look in the other face. Oh, can.
The CFRP bar isn't here.
Okay.
And the
Okay. Oh. So this is the bar. So this is the meteorite. And well, do you see? We have the steel bars. We have the laminates. And this is the bottom face, and well, this is one of the flexural cracks, the principal flexural cracks, and then the propagation, and we can see in the bottom. Okay, so We can interrupt it. Okay, so, well, many thanks for your attending, to have attended this event. Well, um, thanks for being with us, and I think it was a great moment because we realized that the NSM uh, flexural strengthening technique is quite efficient for increasing the load carrying capacity of real beam. So this is, I should say, a real beam. And what is amazing is well, the, the, the values, mainly in terms of maximum load and maximum deflection, is almost the same. So in both beams, which is extraordinary. So okay, so we will be in touch. Now we will post-process results in order to make the comparison or estimate the predictions of the participants and uh, verify what is the winner in both classes of in both groups of participants. So the one group using analytical models and another group with numerical models. Many thanks. Okay, bye bye. Have a nice day. Bye bye.